Have you ever changed your mind after learning something new? Maybe you thought it wouldn't rain today until you saw the dark clouds. That simple shift in thinking is exactly what Bayesian interference is all about, updating beliefs as new information becomes available. Good day. In this video, we will be talking about Bayesian interference. I'm Raymond and I'm gonna give you a brief overview on what Bayesian interference is. Bayesian interference is a way of making statistical inferences in which the statistician assigns subjective probabilities to the distributions that could generate the data. These subjective probabilities form the so-called prior distribution, and after the data is observed, Bayes' rule is used to update the prior, that is to revise the probabilities assigned to the possible data generating distributions. These revised probabilities form the so-called posterior distribution. So in simpler terms, Bayesian interference is a method of statistical inference that uses Bayes' theorem to update the probability of a hypothesis based on a new evidence. Here is a simplified equation of what a Bayesian interference is. This says that new belief is equivalent to the prior belief times the likelihood of the new data. In Bayes' theorem, this is written as this presented on the screen. Updated probability or the posterior is equivalent to the likelihood of the data given the hypothesis times the initial belief or the prior divided by the total probability of the data.
Imagine you're diagnosing a rare disease. You begin with an initial belief about its prevalence, which is the prior, then as you observe patient symptoms, which is the data, you update your belief to inform or to form the posterior. This is the heart of Bayesian inference, and its impact spans countless fields. First, it incorporates prior knowledge, ensuring existing insights inform new evidence. Second, it enables continuous learning, allowing models to evolve in real time, crucial for domains like finance and epidemiology. Third, it handles uncertainty explicitly by delivering full probability distributions rather than a single point estimate. Fourth, it offers flexibility in complex scenarios. Think hierarchical models, missing data, or small sample studies. Finally, Bayesian inference guides decision making under uncertainty by minimizing expected loss or maximizing expected utility. Unlike classical statistics, which often ignore prior information and yield fixed estimates, Bayesian methods deliver a richer, more adaptive approach. Embracing Bayesian inference empowers us to make smarter, more informed decisions in an unpredictable world.
Hi, I'm Pau. And in order to help you understand how Bayesian inference works in practice, let's take a look at three real-life examples. First, we have medical diagnosis. Doctors often use Bayesian inference to update the probability of a disease based on new test results. For example, a patient gets tested for a rare disease. Even if the test is 95% accurate, if the disease is very rare, the chance that the patient actually has it may still be low. Bayesian inference helps calculate the true probability considering both the test accuracy and the rarity of the disease, or also known as the Bayes rate. Next, we have weather forecasting. Meteorologists use Bayesian methods to update weather predictions as new data comes in. For example, if it's cloudy and humid, the forecast model might increase the probability of rain using Bayesian updating with current conditions and past patterns. Lastly, we have legal reasoning. In court, Bayesian inference can help quantify how evidence changes the likelihood that a suspect is guilty. In this example, basically this process helps jurors and legal professionals avoid overestimating or underestimating the impact of new evidence. It also discourages jumping to conclusions based solely on emotionally persuasive data like a DNA match without context. That's all, and the application of Bayesian inference will be discussed by the next person.
Let's now move on to the applications of Bayesian inference. In simpler terms, Bayesian inference is all about updating our beliefs as new data comes in. But how does that work across different fields? For example, in machine learning, Bayesian methods are great in handling uncertainty. This is especially important in areas like medicine, where it's not about making a prediction, but knowing how confident we are in that prediction. And in business, it helps companies make these smarter decisions even with limited data by combining it with what they already know, such as seasonal trends or expert opinions. And in bioinformatics, they're used to analyze gene activity. And also, in expert systems, they help make decisions under uncertainty just like a human expert would. So bottom line, whether it's healthcare, finance, or AI, Bayesian interference help us make better and smarter decisions, especially when the data isn't clear.